Hi, everyone. Good evening once again. Welcome to the session. Hope you're doing good. And let us start with the session. As part of the value-added sessions that we are trying to conduct here, um, thanks to 360DigiTMG, we are looking at various domains. And as part of this session, we are looking at geospatial data and how analytics is actually transforming this GIS domain. So what are the various applications? What are the standards that we have to look at, right? These are the various things that we're trying to learn as part of the sessions. So ultimately, we are trying to look at geospatial data analytics. Now, as part of this, we try to understand the definitions of GIS. It's nothing but ultimately details about the coordinates, geographical locations of the Earth. And this all started with the information being tracked for pandemics, outbreaks. Epidemiologists started using the GIS data to track down on the cause of the outbreak. This was the story that we discussed way back in 1854. We had this issue in UK, London, and John Snow, Dr. John Snow, he was the person who was responsible for coming up with this solution, where he started using a dot map. He created a dot map to locate all the issues that have occurred in, the cases that were recorded in specific scenario. This epidemiologist, the pandemic issue. And later on, it was tracked down to identify that the issue was because of a tap from which the water was consumed. That's how the cholera was actually spread. And this was initially not recognized, but later on, after a few years, the competitor of John Snow, he had to admit that, yes, this was right, the analysis which is true, and the results were accepted. And then we also talked about the application of the GIS data in various domains. This is one such example, which is 2012 elections. Right? And then we also have the various areas where these are the various areas where the geospatial analytics can be used. Then we talked about the various types of data that we will be looking at as part of the geospatial analysis. And one such data that is very, very interesting is the remote sensing data that we can capture. The remote sensing data that we are looking at, right, it basically allows us to capture the data, the geographic data, which otherwise would consume a lot of time and money to track and identify all these locations, map them, find the coordinates, find the distances. So it's going to be a very costly affair, right? So remote sensing was actually a revolutionary approach, and this helped the geospatial analysis to cut down the costs, and in fact that encouraged individuals and organizations to start looking into the geospatial analysis. But the problem here is data will be in a two-dimensional aspect. And along with this, we also used digital elevation data that would convert this data into a three-dimensional data form as well. Digital elevation model. And there are many standards that we will see with respect to the geospatial data. And we also need to understand the different types of data that we will look at when we are trying to do geospatial analysis. The broad categorization of the GIS data or geospatial data can be put into raster and vector data types. Otherwise, the geospatial data can be in any format, file formats. We'll be talking about that. In fact, we talked about that. It has many file formats, and any data that we see which has location, right, geographic location, can be treated as geospatial information. So if I have to put it in very simple terms, anything that can be drawn on a map, right, any coordinates or any data points, can be considered as geospatial data. So all we need is location. Now, if I talk about the broad categorization, we have raster data and vector data. Raster is nothing but an image data. Vector is the data points representing those images, the coordinates which can be identified on a map. So raster is nothing but image data. It has pixels, and each pixel value will have certain significant value. It basically talks about the color, shape, right? These kind of corresponding values will be there for each pixel. The advantage is that in raster, the data is very big. It will have same size and same shape for the cells. And raster data is generally your continuous data. We can talk about this as a continuous data. Whereas vector data, this vector data is basically nothing but coordinates, X and Y coordinate that can be identified on a two-dimensional space. It generally displays latitudes and longitudes, geographic locations. These are some of the examples. We will be able to identify the differences in the temperatures, air pressures, elevations, right? Then we talk about precipitation in various locations, soil erosions, right? All these things are basically captured using raster data. Whereas vector data, you'll be able to identify rivers, roads, right? Borders, these kind of things, the bridges. So these are the specific data points that can be mapped on the data, two-dimensional data space. Then these are different file formats, right from spreadsheets, right, to comma separated values, to tab separated values. All these are different data types that we can see. You can basically look at various options that you are having here, right? And in fact, I have not covered all the other things also. We do have specific data sets or data types that we can talk about. These are also, these are specific for geospatial related analysis. One of the files is called as shape files. The KML files. Then we have geo packages. Then we also have GeoJSON, right? And from a visualization perspective, we also have TIFF files. You can also call it as GeoTIFF. So these are the different types of data that you probably will be seeing specific to geospatial data. But as I said, all of these are broadly categorized into raster data and vector data. Among all these different data types, shape files is something that is most often used, right? And this is a vector data, right? We can talk about shape files as geographical vector data. Next, if I have to look at the other files, the shape files, the extension is .shp, and it is a specific structure in itself. Okay, so this is basically talking about a geometry. Okay, we also have something called as SHX as well. This is a positional index, right? It talks about index of the geometry that we are talking about here. All right, and this is basically having a separate format altogether. And these are your shapefiles. Then we also have another very common file, which is JSON. I'm pretty sure you might have already heard about JSON file format. It's called as JavaScript Object Notation. It's an open standard format. Generally, it is used for communicating the details, the data points between database backend and frontend. Right? If you have a web page, then the data can be moved using JSON formats. Right? So this GeoJSON is basically an extension of the JSON format, specifically used for storing the geographical features. Ultimately, JSON works on a simple logic of key and value pair. Right? And these are very easily readable and all that. And GeoJSON is something which is very simply used. We can either have .json or .geojson extension. Okay. Then we also have geo packages and KML. If I talk about KML, this is markup language. It's like your HTML, right? The XML, these kind of things. KML basically is called as keyhole markup language. K stands for keyhole markup language. This refers to basically the data which is probably used by areas where web pages and all those things come in the picture. You will have a host application like Google Earth, for example, and you can use this KML data on top of that. It is based on markup language, XMLs. Okay, so that's the keyhole markup language definition. And you will have extension as .kmz, not KML, but KMZ. So these are KMZ files. It's nothing but zipped format. Okay, so it will always be a huge data, right? So it will always be compressed format. So we'll have .kmz. Next, we have the geo package and geotiff libraries. Geo package is basically a library which is coming from open package called as OGC. We discussed yesterday. OGC. This is Open Geospatial Consortium. Consortium. We will probably talk about that. This is right, the Open Data Forum, OGC, and within that we have Geo Package. In short, it is also called as PKG. And the fact is that Geo Package can have both raster data or vector data. Okay, this is probably some of the recent types of standards, recent standards in geospatial data. In early or mid 2000s, this 2010s, in fact, Geo Package has come into picture. The another very important point that you need to look at with respect to Geo Package data is that the format was specifically designed keeping in mind how we people are transforming from laptops or your systems, desktops to smartphones. So from mobile users' perspective, the package, this data set has been defined. Okay, so that's about the image data, geo package data. Then we also have GeoTIFF. TIFF stands for a tagged image file format. This is one of the image file formats. It's called as like PNG you have, right? So tagged image file format. We call it as GeoTIFF, in fact. These are specifically used for geospatial data, right? So yeah, that is something that you get as a tag, geographic tagged image file format. This is an industry level image standards that are used for GIS or remote sensing data. Right? All the image sensing systems or all the GIS systems that we basically have, the packages that we have, they use GeoTIFF format. They're compatible with GeoTIFF. We also have JPEG standards also. Along with GeoTIFF, you'll have JPEG. It basically has something called as JPEG 2000. Right? It's basically one of the raster forms of raster data, categorized form of data. And it allows us to compress the image file, JPEG 2000. It doesn't stand with .jpeg. This is not the format. JPEG 2000 goes with JP2. That's the extension. Similarly, we have a lot of huge file formats that can be used. Enhanced compressed velvet, then ESRI grid. ESRI is kind of a very, very popular standard organization that comes up with geospatial analysis. We also have, if I talk about satellite imagery data, then again, there are different formats. Right? So a huge list is there. These are all typically defined for your geospatial data. All right. So that's basically how we can see the data. I'll talk about shapefiles, and I'll be kind of giving you some examples on how these shapefiles can be read, what all various things we can do with respect to different formats of data, right? How we convert from one format to another format. Probably we'll try and look into those aspects. But as part of today's session, I want you people to get the basic knowledge with respect to data analytics standards. When we talk about data analytics, right, if I have to generalize this, it's basically a study which brings in quantified techniques, study using quantified techniques to extract some meaningful information from the data. Right? It's a study or a process which allows us to extract meaningful information from the data. The analytics that we are basically looking at from a general perspective can be categorized into 4 levels or 4 stages. One is descriptive. The other one is diagnostics. These two are coupled together. Then we have predictive, and then prescriptive. Prescriptive is more like a solution development. So descriptive, diagnostics, predictive, and prescriptive. These are 4 levels of analytics that we can perform. For example, we are trying to, we did look at the pandemic, cholera outbreak way back in 1854. Dr. John Snow, Mr. John Snow has come up with a dot chart where he tried to map the taps in a locality and the cases that were registered. Right? These two were plotted on the map, geographical map for that particular area. And then they tried to analyze on which tap had more, close by had more cases registered. So they eventually tracked down to identify that there is a specific tap from which the people were consuming water. They were getting the cases. In those households, there were 14% chances of having more cases. That was the analysis that was performed. So we are talking about here a scenario of descriptive and diagnostic analytics. from a geospatial analysis perspective, this is a classical example of identifying the cause of the outbreak, pandemic, right? Falls under this descriptive analytics stage, descriptive and diagnostic analytics stage. Right? Then we generally see the forecasting of, let's say, floods. We talk about, let's say, the rainfall. These are all predictive analytics cases, right? In which area there might be more rainfall. So by looking at the various factors, we'll try to identify where the clouds get accumulated for, right, these kind of scenarios, or tornadoes, or we can talk about tornadoes also, tornadoes or the cloud bursts. These are all some of the examples with respect to predictive analytics. Prescriptive, of course, is basically the solution that we try to give. Given the conditions, what solution we can give. That's prescriptive analytics for us. So these are the cases that we talk about. But whenever we speak about these analytics, in general, whenever we are trying to deal with data related projects, then the standard process has to be followed. The standard process basically speaks about the industrial standards that have to be followed when you are working on a product or a service or a project which involves data to solve a business problem. So we have CRISP MLQ methodology. This is called as cross-industrial standard process for machine learning with quality assurance. Okay, so this is an example for dealing with your database. And it is cross-industry. Across all the industries, we will be applying the same standard process. And it contains these 6 steps. The first one basically speaks about gathering the requirements and understanding the requirements. Unless until you understand what you have to do, right, we will not be able to provide an appropriate solution. Right, so that's the first point. Along with this business understanding, right, what exactly we need to resolve or what is a business problem, we also look at data related challenges or data related standards that have to be followed. Because ultimately the project is developed using data. I mean, without data, there's nothing, right? So using data, we will have to try and build this. So what are the various conditions or challenges that we will have with respect to data? For example, in geospatial analytics, we are speaking about raster data and vector data. These are characteristics. So what is the data that you are going to work in a given scenario? Right? That will basically allow us to implement an appropriate solution in that business case. The techniques that we are using, right? So all these things will matter. Then comes the cleaning part. Now, if your data is a very simple flat file, and you're talking about a generic business problem statement, then we need to see what kind of challenges the data that we have received has. For example, in politics, the example that we talked about, right? 2012 US presidential elections. What if, right, data was not available? I mean, we had so many states, so many, right, volunteers participating in this surveys to basically gather the data. We need to conduct surveys. So we get a lot of data, but there may be cases where a lot of fields in the questionnaire might not have been filled by the customers, I mean, by people. Right? So if you're asking 10 questions in the survey, right? 10 questions in the survey. You may not expect everybody to fill every point, right? It's good if you get the data, but there may be scenarios where a lot of people don't respond to all the questions. So that means there will be missing data. Now, what you do in that missing data case? In fact, identifying the missing data itself is a task. So once we get the data, we start looking into the pre-processing. Right? We basically look into pre-processing stage. In this stage, we are basically trying to do cleansing. Right? We try to do data cleansing. And as part of the data cleansing or organizing or cleaning, one of the steps is identifying that there are missing values and then try to ensure that those missing values are updated or handled. Now, this process of handling missing data in general is called as imputation. Okay, well, I'll talk about that. So likewise, we may have various other challenges. Now, all this is to be done at the first stage. Before we actually implement any solution, this is what we need to first do. So I have given an example here with respect to missing values. So what would you want to do if the data is missing? As I said, there's a solution called imputation. Imputation is nothing but substituting some value in the space of that missing cell. Right? So for example, in the presidential elections, right, in politics, you might want to get information about, let's say, the feedback with respect to a specific political party, right, Republic Party in US. We don't get that information. So what you do, maybe you will look into the past and then try to get the aggregated information. Right? You might want to take the data from previous instances. That's a safer bet rather than not having any data. Right? We're assuming if we can get the original data, then nothing like it. We'll always try to use the actual data. But we may not have the original data at any given point of time. All right. So that is one challenge that we probably have to work with. We may have certain cases, we may have exceptional values. Now you might want to talk about distance calculations. Okay, in geospatial analysis scenario, we might want to talk about distance calculations. So we are basically trying to identify distances about different right, aspects. For example, that outbreak case. We were trying to identify, John Snow, he was trying to map the cases, right, on a geographical map. If I talk about that, let me show you. I'll use that as a reference here, the image. Yeah, so you can see it on the screen now. This is the dot chart that, right, or dot map, you can say, which was used by John Snow. What did he do? What did he do is he marked tab and then the registered case. The distances, we are trying to measure the distances between a case to another case, distance from the tab to these cases. We may have multiple tabs, right? So these are distances. Now might have a scenario where there is a tab here And there is, just assume that we have a case where, there is no other map. Assume that there is no other tab. This is the only tab, or let me put it this way. This is the only tab that we have. So you can see a lot of cluster of cases surrounding that area. Okay, this is fine. But you may see that there is one or two cases somewhere here. So the distance here is very small. It makes sense, right? But this is a very, very huge distance, right? Far off distance, far off location. But here also we have a case. Now this could be an exceptional case. When you look at the distance compared to other locations, from the tab to the distance, right, from these locations, you might see all the distances clustered to a small number. Maybe I'll put some numbers here, right? So let's say these are lying between, say, ranges, the value ranges from 5 to 10 meters, assume, or whatever that is, right? 5 to 10 meters. But if you talk about this distance, maybe this is 1 kilometer, right? 1,000 meters. So you can see, comparing to all the rest of the values, this location is an exceptional case. So when you look at the numbers, you will see that this number is very, very high compared to rest of the numbers. This kind of numbers are called as, this kind of values are called as outliers, right? Outliers. So when you have these kind of exceptional cases, what would you do? The solution implementation is complete subjective decision. It's a trial and error based solution that we are looking at here. But the cases is something that you need to identify. These are different cases that you will see, and you will have to identify these cases. Solution is subjective. Depending on the situation, the analyst is going to come up with a specific solution for that. Right, so this is subjective decision. Similarly, if I have duplicates, obviously I don't want a duplicate value, right? You cannot say that there are two entries for the same point. It doesn't make sense, isn't it? If the value is duplicated, you might want to remove that. Then in certain cases, your data could be non-numeric. If your data is non-numeric, then for mathematical calculations, you want to convert this into numeric form. Now, again, when you talk about converting non-numeric data to numeric form, there are many ways to do that. For example, if you're talking about tab, I may say tab 1, tab 2, tab 3, like this. So rather than saying tab 1, tab 2, tab 3, I can probably say 1, 2, 3. Right? This is one way. Right? Or we can probably create multiple columns for tab 1. We'll say whether the water has been used from this particular location or not. 0 means not used. 1 means used. So for a specific location, for a specific house, the tab that was used is tab 2. You will see zeros and ones there. For another, probably for some other house, the tab 1 was used. Ones and zeros will be there. So this is nothing but house 1. We talk about tab 1. House 2, tab. This is tab 1. This is tab 2. Right? If this is the case, then you'll be converting this into like this. There are certain terminologies. This is called as this approach of having multiple columns for the single column is called as one-hot encoding. The gold standards that we are talking about with respect to analytical solution development. This approach where you're giving numeric values is called as label encoding. If you feel that these values are having natural order, for example, layers, right? If we talk about Earth crust layers, then probably layer 1, layer 2, layer 3, you might want to put them in the numeric order because it has order, right? Or vegetation, for example, highly vegetative value, the deserts. So you might want to give some kind of a coloration or value to this color. That's your dummy variable creation. The best example is colors and the numbers for these colors. Right? We want to speak about weather forecast. Right? So the colors signify how strong the winds are blowing in a specific region or how heavy the rainfall is there in specific area. So the numbers, the values are tried to be converted into images, and those images will have a specific value. That's your raster data. We also have something called as transformation. We also have something called as standardization and normalization. All these are the data pre-processing steps. So once we try and understand the requirements, then we collect the data, and for geospatial data, there are different standards. Ultimately, we are going to collect the data in one of the two forms. One is raster data, the other one is the vector data. And depending on the data that we're collecting here, we further look at the data pre-processing, what challenges we have in this data and what pre-processing can we do. And when we talk about pre-processing, it contains cleaning. There might be unwanted data in unwanted format. You might want to clean that or transform that. Dummy variable creation is one such example. You might want to organize the data so that we understand the data better. For example, a location is there. Rather than trying to take this location, you might want to use latitude and longitude as an alternate option. So these are all different use cases which allow us to basically convert the data into an appropriate format that is required for us to handle that data. Right? So for example, in some cases, latitude and longitudes will be converted to a location so that we can pinpoint them in the map, right, city-wise. In some cases, these locations, the names, might want, you might want to convert them into coordinates, latitude and longitude. So this is basically requirement-driven strategy. Once these requirements are done, once your data is analyzed, then we go for the next step, which is machine learning. Of course, we also have to do EDA, that is preliminary data analysis. We basically have to understand the characteristics of the data. Only after doing this pre-processing steps, we can move to the next round. That is our next step. That is your machine learning implementation. Analytics, right? So machine learning implementation will come into picture. Now, there are many types of applications, standards in machine learning, which are broadly categorized into two parts. One is unsupervised. The other one is supervised. The difference between these two is here, there is no label. Here we will have label. And because label is here present, we will know what is that data volume, right? The characteristics. And using this label, we will try to train the computer, the machine, so that it can do prediction when input data is given. Label is like the answer to the question. Question is your data. So we already know the answer. So you're training yourself, or your computer is getting trained on this question and answer bank. Using this information, when we get a new question, we will be able to answer the question, or we should be able to answer that question. That's your supervised learning. Whereas unsupervised learning, we don't have any label. So we are basically trying to understand the characteristics of the entire data set. And then we try to label it. Labels are not. Right? For example, we are talking about vegetation. Different areas have different vegetation capabilities. We don't know. And right upfront, we will not have any information on which area is probably good for cultivation, which area is not good for cultivation, what kind of cultivation, right? All these things, we are not sure. But when we try to gather all the data points and aggregate them together, we probably will be able to identify that there is a group of locations, right? A group, right? A specific location, group of coordinates. All these form a cluster, by the way. Group is nothing but a cluster. And that cluster says the location is more, more suited for doing cultivation. Whereas there probably could be another area where the vegetation cannot be grown, right? The land is not suited for cultivation. So when you look at the data, and when you segregate the data and look at the data, you will be able to give the label, like this location will not be able to cultivate. This location, the chance of cultivation is higher, right? The richness in the soil, or the conditions, the water levels, could be anything. We are saying, hey, in this area, in these areas, there's good chances of having a vegetation. So this is called as unsupervised, where you're trying to do only descriptive analytics. And when you say descriptive, automatically diagnostics is part of this. Whereas in supervised, we are trying to do only predictive analytics, right? So this is only descriptive, this is predictive. And whenever we talk about predictive analytics, we will get a mathematical equation like this: y is equals to f of x, where y is the label, the variable of interest, and x is the input. And we are trying to derive the relationship between these input set of factors and output. All right, so that's about your predictive analytics equation, where f is trying to represent the relationship in a mathematical notation. Right? It's trying to understand the relationship between y and x. So that's about your data mining concepts. Now, once we get the equation, it's not done. Once we are getting the equation, the solution development is not done. Whatever the equation that we are getting, is this equation good? Right? That is something that we have to evaluate. We need to check, right? Whether these values that we are seeing are good or not so good. Right? So that's the evaluation, and there are metrics which basically are calculated, which allow us to declare whether the equation is appropriate equation, a good equation, which can represent the relationship in the business case or not. All right. And then once these are done, then comes the deployment part. And for geospatial data, the deployment is going to be another challenge, because right, it's more like a dynamic kind of a visualization, and large amount of data has to be used as a backdrop. the maps that we are talking about, right? So all the coordinates and all those things have to be used. And on top of that, we are basically trying to give the information. And finally, we also have to look at the solution. We monitor and we constantly keep a maintenance eye on the solution that we have developed. So monitoring and maintenance will be part of the solution. So these are the high-level steps that we'll have to do with respect to geospatial analytics. Now, when we talk about metrics, I'll come back to this. When we talk about metrics, okay, let me put it this way. The analytics that we are speaking about, and in that, when we specialize on or when we specifically talk about, when we specifically talk about supervised learning, we said that it is trying to do predictive analytics. It's nothing but we're trying to do predictions. Now, this predictive analytics will basically performed on labeled data, where Y is the label here. And we're trying to understand the relation between the input factors and the label using mathematical concepts. All right, so this is about your predictive modeling. Now, what is the value that you're trying to predict is going to be an important question. If you're doing predictive analytics, then the equation should allow us to get the result that we want. And Y is equals to f of x. This Y is label. And this is the label data. All right. Now, this labeled data has to be evaluated using certain metrics, right? The equation that we are getting has to be evaluated for the label that we are trying to get. So if the label is from a numeric standpoint, if the calculation that we are doing is for a numeric value, then after doing the calculation, we will be able to try and map on how close we were with respect to the calculation on the historical data. In historical data, we have this label data, right? So this is basically the original value, and this is your predicted value, and we're trying to measure the difference between them. But if this is numeric data, this difference is called as error in prediction. Lesser the error, better the model. Okay, that's basically how we interpret. But we also have non-numeric case. And we're trying to predict this non-numeric case. When we're trying to do the prediction for non-numeric case, then the data that we are trying to come up with has to be evaluated by comparing it with the actual value of the same record. Now, because this is non-numeric, right, we cannot do a mathematical calculation. We'll only do a comparison-based analysis. So we say y hat, that is predicted value, is equal to the actual value. When you say double equal to, the answer could be either true or false. Right? True or false. Now, we will be using Python for doing the hands-on. And when we do that, Python is treating the true as 1 and false as 0. This is a standard that Python uses. Now, if the values are same, for example, you're saying rainfall will be there. Okay, rainfall, assume that we are predicting rainfall in a specific locations. So I have various locations. And we are saying whether rain will fall or not. So you might have predicted certain values here. Let's say you say no rain. Now, when you actually look at the results, this is, let's say, predictions that we are doing. But in the historical case, we have seen that, yes, this location has not been affected by rain. There was no rain, right? So assume that is the concept. The same location, we are saying no rain. So in actual, we do not have rain, and the model that we are using, the equation that we are using, is also saying that no, there will be no rain. That means the prediction that you are doing is equal to the actual value. Right? The prediction that we are saying is basically saying the predicted value is equal to the actual value. So we will get true here. Now, what if we predicted that there will be no rain, but in actual there is rain? What in that case? What should we do? So here we are saying rain, for example. Here we are saying no rain again, the prediction. This is a false. This is a false statement. Similarly, we have no rain, actual condition, but rain is the prediction condition. This is also a false condition. But when you have rain and your model also predicts rain, then that means this is a true comparison. So when you're trying to predict a non-numeric output, we will have to do the comparison with respect to the actual value and the predicted value. Right? And if these are same, the values are same, then you will get true. If their mismatch is happening, then the value will become false. So here we will try and look at how many times the model has correctly predicted true values. Summation of true values. This gives us accuracy. Whatever we are predicting, it is same as the original data. Right? So that means your model is giving us good results, predicting the results as expected. We can also calculate overall error rate or false rate by adding these false comparisons. So when your data is non-numeric, we can either use the overall error or accuracy. Whereas if your data is numeric, then we will only have error calculation, and for that error, we use something called as RMSE. That basically speaks about root mean square error. RMSE. These are standard two ways that we will be using for doing model evaluation. Along with model evaluation, we also, when we are developing the models, we will try to do tuning. When we verify how good the model is working, we'll also come to know that it probably is not working right in a specific way on right certain things or certain cases. So overall, in order to get a good performance, we will further refine the model. I would want to use the word refining, right? So we refine the model, that is nothing but altering parameters, altering inputs that we pass to the model. These are called as parameters. These parameters which are allowed to alter are called as hyperparameters. So by altering the values of these parameters, we will be able to get the result. Here we are doing tuning. Now, once the tuning is done and once the model is evaluated here, then we go for the next stage. So this is basically the high level life cycle of implementing a solution using the data. Right? A data analytics or a data science job will basically talk about descriptive analytics or predictive analytics. And the CRISP MLQ methodology that we are seeing on the screen, the standard process, it is applicable for both right, your supervised learning techniques and unsupervised learning techniques. That is basically means we are talking about descriptive or diagnostic analytics and predictive analytics. Right. So this is the overview. And in the next class, we will try and see manipulating the GIS data. Right. We'll play around with GIS data in Python. Now, for getting the hands-on in Python, I would recommend you people to go through the Tame the Python sessions, which are conducted on YouTube Live, just like how we are attending these sessions on the 360DigiTMG channel, on this YouTube channel from 6:30 IST to 7:30 IST. You will have the Tame the Python sessions going on. To get better knowledge, better hands-on with respect to Python, you might want to attend these programs. With that, I would try and conclude for the day. And in the next class, we will look into some kind of GIS data and how do we manipulate that data. Until we meet again tomorrow, thank you so much. Good evening and stay safe, friends.